Hello everyone. Today we are going to learn the sound field law of ultrasonic shear wave. There are 3 points in this section. 1. The generation of shear waves. 2. Shear wave sound field. 3. The actual sound field. The teaching objectives of this class are: 1. Master how to get shear waves through wave mode conversion. 2. Learn to analyze the characteristics of shear wave sound field by using imaginary wave source. 3. Be familiar with the difference between actual sound field and the ideal sound field and understand the reasons. Now let's talk about the sound field law of shear waves. In actual ultrasonic testing, shear waves are converted from longitudinal waves on the detection surface. At this time, the ultrasonic field is the sound field broken at the interface. In the first medium, it is a longitudinal wave sound field, and in the second medium, it is a shear wave sound field, as the picture shows. For the convenience of research, it is assumed that there is an imaginary wave source which directly generates shear waves and enters the second medium straight without changing the propagation direction. In this way, the laws of the longitudinal wave sound field can be directly introduced into the shear wave sound field. The hypothetical wave source needs to satisfy 2 conditions. 1. It is the same as the actual wave source acting area at the interface. 2. The distances L1 and L2 are both located in the near field area. According to the above assumptions, it is not difficult to calculate the area of the imaginary wave source. Fe is equal to F0 multiplied by cosine beta slash cosine alpha. In this formula, F0 is the area of the actual wave source. Alpha is the incident angle of the longitudinal wave, and beta is the reflection angle of transverse wave. The distance L2 from the imaginary wave source to the incident point. L2 is equal to L1 multiplied by tangent alpha slash tangent beta, where L1 is the distance from the actual wave source to the incident point. According to the explanation of the last class, it can be known that in the second medium, the length of the near field region is n is equal to n2 plus L2. In the formula, n2 is the length of the near field region when there is only the second medium, which can be calculated according to the formula of the near field region of the longitudinal wave sound field. Sound pressure on the center line of the shear wave sound field. Similar to the longitudinal wave sound field, it can be known that when the distance is greater than 3 times the length of the near field, the sound pressure P is equal to Kp0 Fe slash lambda S2 multiplied by Xe, where Xe is the distance to the imaginary wave source, which is greater than 3 times n2. The laws of the shear wave sound field just now are very similar to the longitudinal wave, but due to the spread of the longitudinal wave, the diffusion of the shear wave sound field becomes more complicated, and it is not completely symmetrical about the center. The discussion is divided into two sections below. In the plane, as shown in the figure, it is divided into the upper half diffusion angle and the lower half diffusion angle with the center line of the sound beam as the boundary. We can figure out from the picture the upper half diffusion angle, zeta up, is equal to beta 2 minus beta. The lower half diffusion angle, zeta down, is equal to beta minus beta 1. The second expression is zeta 0 is equal to arc sine, open parenthesis 1.22 lambda slash d 0 close parenthesis, which is the half diffusion angle of the longitudinal wave in the first medium. The third expression is based on the application of Snell's law to the sound waves. Snell's law is the law about the directions of diffracted light. It is firstly discovered by Dutch physicist W. Snell in 1621 from experimental observations. This law is also called the law of refraction. Snell's law is actually the same as the law of refraction of light. By jointly solving the above three expressions, the upper and the lower half diffusion angles of the shear wave sound field can be obtained. You will find that they are not equal, and it can be seen that in the plane of the diagram, the shear wave sound field is not symmetrical about the center. In the plane perpendicular to the paper and passing the center line of the shear wave sound field is symmetrically distributed, and its half diffusion angle is the same as the longitudinal wave diffusion angle, and its half diffusion angle zeta 0 is approximately equal to 70 times the shear wave wavelength divided by the wave source diameter. Taking an example to analyze the degree of diffusion of the shear wave sound field. Example 1. Use a 5.0 mHz phi 12 mm K2 shear wave oblique probe to detect a steel workpiece. Knowing that the plexiglass longitudinal wave sound speed in the probe is 2730 m/s, and the shear wave sound speed in steel is 3230 m/s, find the half diffusion angle of the shear wave sound field in the steel. First of all, pay attention that the K2 in the title refers to the tangent value of the shear wave refraction angle in the steel beam too. This is the regulation of our country, and we will talk about it later. That is, tangent beta s is equal to 2. Phi 12 means that the diameter of the sound wafer is 12 mm. The plexiglass in the probe is the first medium, and the steel is the second medium. The following calculation is performed using the analyze just now. First, calculate the wavelength and the shear wave refraction angles in the first dielectric plexiglass and the second dielectric steel, respectively, beta s. Shear wave refraction angle in the second medium, beta s2 is equal to arctangent 2 is equal to 63.4 degrees. The incident angle of the longitudinal wave in the first medium, alpha, is equal to 49.11 degrees according to Snell's law. The half-diffusion angle of the longitudinal wave sound field is theta is approximately 270 lambda L1 slash D0 is equal to 70 multiplied by 0.546 divided by 12 is equal to 3.185 degrees. The angle of refraction corresponding to the upper edge of the shear wave is zeta2 is equal to 75.4 degrees. Therefore, the upper half diffusion angle of the shear wave is zeta up is equal to 69.4 minus 63.4 is equal to 6 degrees. The refraction angle corresponding to the lower edge of the shear wave is beta 1 is equal to 58.2 degrees. Therefore, the lower half diffusion angle of the shear wave is zeta down is equal to 63.4 minus 58.2 is equal to 5.2 degrees. It can be seen that the entire diffusion angle of the shear wave sound field in the plane shown in the figure is theta 1 is equal to theta up plus theta down is equal to 6 plus 5.2 is equal to 11.2 degrees. The overall diffusion angle of the shear wave sound field in the plane perpendicular to the blackboard is theta is approximately equal to 2 multiplied by 70 lambda s2 slash d0 is equal to 140 multiplied by 0.646 divided by 11 is equal to 7.536 degrees. According to the above calculation, in the plane shown in the figure, the upper diffusion angle of the shear wave sound beam is 6 degrees greater than the lower diffusion angle of the 5.2 degrees. The entire diffusion angle is 11.2 degrees, and the entire diffusion angle of the shear wave sound field perpendicular to the blackboard plane is 7.536 degrees. The former is greater than the latter. So now we can imagine that the longitudinal wave radiated by the disk sound source undergoes refraction and wave mode conversion, and then the shear wave sound field section should be elliptical. And the same 5.0 MHz phi 12 mm straight probe produces longitudinal wave sound field diffusion angle of 13.77 degrees. Compared with the two sections of the shear wave sound field, the diffusion angle of the 11.2 and 7.536 degrees are larger. It can be seen that under the same conditions, the sound beam directivity of the shear wave is better than that of the longitudinal wave, and the energy is more concentrated. Well, that's all for this point. Till today, we have learned the laws of the longitudinal wave sound field and shear wave sound field. It is necessary to point out that this is a theoretical result. The actual sound field is somewhat different from the theoretical sound field, especially in the near field, as the picture shows. The sound pressure on the ideal sound field axis has a series of maximum and minimum values, and the maximum value is 2.0 and the minimum value is 0. Although there are many maximum and minimum values of sound pressure on the actual sound field axis, the fluctuation range of sound pressure is small, and the maximum value is much smaller than 2.0. Only when the distance is long does the actual sound field agree better with the theory. This is because the ideal sound field medium is uniform and non-absorbing liquid, and the sound source does continuously piston vibration. However, pulse waves are often used in actual ultrasonic testing, and most of them are solid media. In addition, the ideal sound field is a continuous wave, which belongs to complete interference in the near field area, while the pulse wave actually used to belong to incomplete interference, and the total sound field tends to be uniform after superposition. Improved, the sound pressure change range is smaller than the ideal sound field, and the extreme point is reduced. In the far field region, due to the small sound positive difference from each point of the sound source to a certain point on the sound beam axis, the wave interference is greatly weakened or even no interference occurs. Therefore, the sound pressure on the axis of the actual sound field is basically the same as that of the ideal sound field. Therefore, when the distance is greater than 3m, the theoretical results are often used in practice. Through today's explanation, I believe that you also have a basic understanding of the shear wave sound field. Finally, several key points should be emphasized. 1. Shear waves are obtained through refraction and wave mode conversion. 2. The shear wave sound field is asymmetrically distributed and its cross-section is roughly elliptical. 3. The sound field of shear waves is more concentrated than that of longitudinal waves. Well, that's all. Thanks for your watching.